we have this equation to solve with tan theta, tan 2 theta, and then some sort of series. So I'm just going to first of all write some terms out in the series to understand it a little bit more. Now cos to the power 0 is just 1, so my first term is going to be 2, and then I'm going to get 2 times cos to the 1, so that's just 2 cos 2 theta, plus 2 cos squared 2 theta, plus 2 cos cubed 2 theta, and so on. In fact, I can factorize out the 2, and you can always do this. You can bring constants out of summations. So 1 plus cos 2 theta plus cos squared 2 theta. Again, I've got to grips with it. I can see it's going to be a geometric series. So A is equal to 1. The common ratio is equal to cos 2 theta. I'm timesing by an extra 1 every time. The sum to infinity is A divided by 1 minus R. So in this case, 1 over 1 minus cos 2 theta. So that means tan theta tan 2 theta is equal to 2 over 1 minus cos 2 theta. Now remember, we're trying to solve for tan theta, so I'm going to try and keep everything in terms of tan. Let's investigate the double angle formula for cos 2 theta. Cos A plus B, I actually talked about this in the previous question too, but I'm just going to talk about it again. Cos A cos B minus sine A sine B, which means that cos 2A is identical to cos squared A minus sine squared A. And I think I'm just going to substitute in for that. So 2 over 1 minus cos squared theta minus sine squared theta, which becomes 2 over 1 minus cos squared theta plus sine squared theta. But 1 minus cos squared theta is sine squared theta, so it actually becomes 2 over 2 sine squared theta, and these cancel, leaving me 1 over sine squared theta, which is then cosec squared theta. So after all of that, that infinite geometric series simply simplifies to cosec squared theta. Great. I'm going to do a couple of things at this point. First of all, I'm going to expand tan 2 theta using the double angle formula for tan. So tan A plus B is tan A plus tan B over 1 minus tan A tan B. So therefore tan 2A is 2 tan A over 1 minus tan squared A. It's worth just knowing that, to be honest, but we've derived it. So tan theta times 2 tan theta over 1 minus tan squared theta is identical to cosec squared. Now cosec squared, we also have, so I'm going to change this and do it in red just to indicate that I'm dealing with some identities here. Right, so how does cosec squared come into it? Well, sine squared plus cos squared is identical to 1. If we divide through by sine, then 1 plus cot squared is identical to cosec squared. So the right-hand side can be rewritten as 1 plus cot squared theta. Now we're getting where everything is essentially in terms of tan theta. 2 tan squared theta over 1 minus tan squared theta is going to be 1 plus cot squared theta. So actually, I'm going to then I'm going to multiply through by 1 minus tan squared theta. And this is an equation rather than identity. So 1 plus cot squared theta times 1 minus tan squared theta, which is going to become 1 minus tan squared theta plus cot squared theta, and then minus cot squared theta times tan squared theta. Now this is actually just equal to 1 because I've got 1 over tan squared theta times tan squared theta. And then it cancels out with this one. So I end up with 3 tan squared theta is equal to cot squared theta, which remember is 1 over tan squared theta. And we're basically there. Tan to the power of 4 theta is therefore going to equal a third, meaning that tan theta is going to be the 4th root of a third, which becomes a third to the power of a quarter, or 3 to the power of minus a quarter. And that is going to be our answer. Now, just one thing I want to comment on. Normally when you take a square root or a 4th root, you need to include plus or minus. But if we sketch out tan theta between the values of 0 and pi over 2, then we can see it's strictly positive. So ignore minus 3 to the power of minus a quarter solution, since tan theta positive for 0 less than theta less than pi over 2. Nice. Now, in part B, we're asked to hence show that theta is between pi over 6 and pi over 4. So tan of pi over 6, this is an exact value to be aware of. It's the same as tan 30. It's 1 over root 3. I'm not going to go into derivations of that here. Please do look it up and learn them. Tan pi over 4 is the same as tan 45, and it's 1. Now, 1 over the square root of 3 is actually less than 1 over the 4th root of 3. The reason being is that the 4th root of 3 is, sorry, that was meant to be the 4th root. The 4th root of 3 is less than the square root of 3. So when we do 1 over it, it's going to swap around. And these are both going to be less than 1. And this implies that tan of pi over 6 is going to be less than tan theta, because that is tan theta, which is less than tan of pi over 4. And I drew a diagram already, but tan is monotonically increasing. That means it just always increases over the interval. I know it has discontinuities. So maybe I'll say over 0 less than theta less than pi over 2. And therefore, pi over 6 is less than theta, which is less than pi over 4. We can just get rid of those tans because if it's smaller like this and it's monotonically increasing, it means the x values will also be like they'll still follow that inequality. All right, an enjoyable trig question. Well done.